Okay, so here we're going to figure out what remainder theorem is and what it's trying to say. So before we get into what that theorem is, we're going to kind of do a little investigation uh, of some things first, and that'll give us some insight into what remainder theorem is going to say. Okay, so here we have our polynomial, some sort of function, 2x cubed minus x squared minus 4x plus 7. And what we're going to do is we're going to divide this with x minus 2 using synthetic division. So if you don't know what synthetic division is, go back to like the videos on the left. There's a video about long division that includes synthetic division. So if all of this, what we're going to do is going over your head, you can click on the video to the left. You should be able to see it. Okay. Wait, on the right. Yes. Okay, so let's do this. So we just set it up to -1, -4, 7, 2. Okay, so for synthetic division, we bring this down. We get 2. 2 times 2 is 4. -1 plus 4 is 3. 3 times 2 is 6. -4 plus 6 is 2. 2 times 2 is 4. 11. Okay. So we got our thing here. So we actually, once we do the synthetic division, in this case, all we're going to care about is this number right over here, this guy. Our remainder here is 11. So this is the only number we're going to care about right now, and we're going to leave this for now. So now we're going to work with this polynomial here, 2x cubed minus x squared minus 4x plus 7. So if you notice, once we did our synthetic division, what we divided our polynomial by was this, x minus 2. So if you remember from graphing polynomials and things, when you saw this in your factored form equation, like the x-intercept is going to be 2. That's the corresponding number to this factor over here. So what we're going to do is we're going to substitute that number, the one corresponding to this, into our function up here. So since our corresponding number for x minus 2 is 2, we are going to substitute 2 into our function and see what we get. So I'm going to write that over here. So f at 2 equals to 2x. Oh, okay. 7, 3. 2 cubed minus 2 squared minus 4x plus 7. This gets us 16. 2 cubed is 8 times 2 is 16. And then 2 squared is 4. Oh. Oops. We should be subbing in 2 here. Okay. Minus 8 plus 7. And this turns out to be 11. So, if you notice, holy crap, these two numbers are the same. Bam. So this kind of raises a few questions, right? Does this work for any divisor we choose? So let's say instead of dividing by x minus 2, we're dividing something like x minus 5 or x plus 4 or like 3x minus 1. If we did the same thing, would these numbers still match up? Would our remainder over here, when we do synthetic division, match up when we substitute the corresponding number in our function? So that's the first question. The second question is would this also work if we change the original function that we had? So let's say instead of x cubed minus x squared minus 4x plus 7, what if we had some other random polynomial and we replaced these guys with something else? Would that still be true? What we're going to do is we're going to tackle both questions at once. So we're actually going to change this to something completely different. And we're actually going to change the polynomial that we started off with. And we're going to go through the same process. We're going to do our division over here. And we're going to substitute the corresponding factor into the function and see if the remainder and the number that came out are going to be the same. Okay, so let's change our function up here. So we have a new function here, 3x cubed plus 5x squared minus 1. It's a little bit different. And then we're also going to change this factor here. So instead of having x minus 2, let's do something different. Let's do 2x plus 3. Plus 1. Let the numbers be slightly nicer. Okay, so we're gonna do the same thing. Let's erase all of this. Okay, so let's do it. Let's do our synthetic. So over here, we can do our normal synthetic, 3, 5, and since we're missing our x term, we're going to put 0 as the placeholder, -1. Okay. Awesome. So, the corresponding factor here is -1/2. Or corresponding number to our factor is -1/2, so we put it over here. Alright, so let's do our synthetic. Bring down the 3. 3 times -1/2 is -3/2. Then 5 plus -3/2 is 7/2. 7/2 times -1/2 is -7/4. 0 plus -7/4 is -7/4. And then -7/4 times -1/2 is +7/8. And then -1 times 7/8 is -1/8. Okay, so here's our remainder. Alright. So, if our hypothesis is true, that means that if we substitute in -1/2 into our function, if we try this, we should get -1/8. So, if we don't get it, then our guess would not be true. Okay. So, -1/8. Oh, wait, no. We're something in -1/2. Okay, so you have 3, -1/2 cubed, plus 5, -1/2 squared, minus 1. Okay, so let's do this. That cubed is -1/8, so this becomes -3/8. -1/2 squared is 1/4 times 5 is 5/4 minus 1. Okay, so if you do our normal fractions, 10/8. Ooh, lo and behold, we have -1/8. Sweet. So we changed both. This is what we did, I guess, as an overview. What we did is we changed the divisors. So instead of x minus 2 in the previous example, we have 2x plus 1 now. We also changed the polynomial. So even though we changed both things, we changed everything that we could, once we do the same process, we still get the remainder and this number to be the exact same. So this will be true for all polynomials and anything that we divide for. So let's summarize what we kind of figured out. Okay, suppose we have a polynomial. I'm going to type this out. Okay. So this is his remainder theorem right now. Remainder theorem says grammar. Okay. What remainder theorem says is the remainder when dividing a polynomial by a factor. So this is the remainder when dividing a polynomial by a factor. What this means is when we divide a polynomial with this factor is going to be the same if we substitute the factor into our function. So we're not technically substituting our factor, but the number corresponding to our factor. So I'm actually going to change this. If we substitute the number corresponding to our factor into our function. Alright, so let's say this, let's go over this one more time. So the remainder, when dividing a polynomial by a factor, so we're talking about when we divide this guy by 2x plus 1, this number is going to be the same if we substitute the number corresponding to our factor, so that refers to this guy, negative 1/2. This number corresponds to our 2x plus 1. If we substitute that number into our function, so that's this guy, those two numbers will be exactly the same. So you might be wondering, what does this mean? What does this mean? So what this means is if we only want to know the remainder, let's say you're doing a problem and you kind of figure out, okay, you just need to know the remainder of dividing one thing or another. We don't need to do synthetic division. We don't have to do this entire long process. All we need to do is we just have to substitute the corresponding number to what we are dividing into a function, and we can find our remainder. So let's say, for example, let's ignore all of this stuff. Let's say we didn't do this. Let's say you want to find out the remainder of 3x cubed plus 5x squared minus 1 divided by this. We just want to know what the remainder is. Instead of doing synthetic division, we can just do this. The corresponding number for 2x plus 1 is negative 1/2. So all we have to do is substitute negative 1/2 into our function, and we can find the remainder over here. And that's all we have to do. Okay, so let's write what we said here in terms of a math notation that we're more used to. So basically, this is something that you might see at school before. So the remainder of f of x, so f of x is our polynomial, divided by our factor, which is ax minus b. So if you're wondering what the a and the b stand for, I kind of already highlighted here. So the a corresponds to the number in front right here, and b corresponds to this number. The remainder of ax minus f of x divided by x minus b, so this guy divided by this, is going to be the same as if we substituted the number corresponding to our factor into our function. So what we did is, to get the number corresponding to our factor, we just divided this number with this number, and we changed the sign. So in this case, if we did the same here, it's just b divided by a, and since we flip the sign, it's going to be positive. So we just have to substitute positive b over a into our function, which is exactly what we said here. So the remainder of f of x divided by ax minus b is the same as if we substituted the number corresponding to our factor, which is b over a, into our function, which is what we did over here. Those guys are going to be the same. And that is our remainder theorem. So today we've been talking about factor theorem. And this actually comes from a specific result of remainder theorem. Basically, if you forgot what remainder theorem was, this is what it says. Basically, if we substitute the number corresponding to a factor into a function, it will give us the remainder when we do our long division. So instead of having to do this big long division over here to get a remainder, all we have to do is substitute the corresponding number for this into our function, and we can find the remainder that way. So what we're going to do is we're going to do this specific example. I set this up in a specific way so we get a certain result, and that'll actually get us insight to what factoring theorem is. So let's do it. Let's get this started. So 4, -2, 6, -3, and we're dividing by 2x minus 1. So in our syntactic division, we put it 1/2. Okay, let's do it. So 4 times 1/2 gets us 2. And then -2 plus 2 gets us 0. 0 times half is 0. 6 plus 0 is 6. And then 6 times 1/2 is 3. And then -3 minus 3 is 0. Okay, so if you notice, the remainder that we got is 0. So what remainder theorem says is if we substitute 1/2 into a function, we're also going to get 0. So let's confirm that. Equals 4 1/2 squared plus 6 1/2 minus 3 equals 2. Oh, this is 1/2 minus 1/2 plus 3 equals 0. Okay, so we have these guys. What does this mean? So if you recall, when you were graphing polynomials, usually our function was in factor form. Something with brackets like this. And we would take these guys, and these guys would be our x-intercepts of our original function. And then before, if our polynomial wasn't in factor form, it was actually impossible to graph. So if we had our function looking like this, we're like, no, we can't graph it, it's too hard, it's impossible, we don't know the x-intercepts. But this result actually gives us an insight into how to do so. So since we plugged in 1/2, it got us 0. That means that the point 1/2 and 0 is an x-intercept. So if we kind of draw a little sketch here, that means that we're going to have a point on our function at 1/2. Therefore, if we were to factor this guy, one of our brackets over here would have to be 2x minus 1. So this is actually really cool because before we didn't know how to factor things like these, besides grouping and all of that. But now this thing where if we substitute that number, it gets us 0. The corresponding factor to the number would actually be one of our brackets, one of the factors of our original polynomial in standard form. And then we can even go further with this, right? Like, what will be the other bracket in this case? Well, since we divided 4x cubed minus 2x squared plus 6x minus 3 with 2x minus 1, the result down here, these represents the quotient of our polynomial, if you remember from synthetic division. So the other stuff in our bracket will actually come from these three numbers. So these ones will actually be 4x squared minus 6. There you go. Okay, so let's go over what we kind of just said here. So what factor theorem says is factor theorem. So if we substitute a number into our function and it equals 0, then the corresponding factor of that number is a factor of f of x. So I guess if we substitute a number into our function, so in this case we substitute 1/2, and it equals to 0, then the corresponding factor of this number is going to be a factor of our original function. So in this case, since we substitute 1/2, the corresponding factor of 1/2 is 2x minus 1. That means that one of our brackets for our function, if we were to factor our original function, is going to be 2x minus 1. And that's what factor theorem says. Let's say this in probably what your high school is going to teach you, like the mathematical way. It's a way of saying it. So if the number we substitute into our function, that's like b minus a, b over a, equals to 0. So if you don't remember or are confused about what that means, b, this guy, comes from number at the very top over here, and our a comes from number at the bottom over here. So if that number we substitute into a function and we get 0, then the corresponding factor of b over a, the number we subbed in, which is basically ax minus b, in this case it's 2x minus 1, is a factor of our function, original function. So that means that we can, if we factor this, one of the brackets is going to be this guy right here. And that is factor theorem. Alright, so here's some examples for factor and remainder theorem, the concepts that we just learned. So over here is just kind of overview of what we learned from the past, I don't know how many minutes, 20 minutes. Now these are the two results. And we're going to use these guys, these concepts, into solving the problems down here. So these are sample problems that you might see in school. And we're going to go through these, and we're going to go through the logic and the thought process as to how to use our theorems over here to solve these problems. So if you're looking for a specific example, there are timestamps below for each one of these questions. That way you can save some time and just click on the timestamp so you get to where you need to go. Alright, let's start this. Okay, so here's our first example. Determine if the following functions have 2x plus 1 as a factor. If not, state the remainder. So we have these two guys. So our goal is to determine whether or not this guy is going to be a factor of both of these polynomials over here. So we can actually do this using what we know about factor theorem. So factor theorem says that if we sub in a number, let's say n equals 0, then the corresponding factor to that number is a factor of this. So it actually also works the other way around. If we want to find out, in this case, 2x plus 1 is a factor of a polynomial, then we just have to substitute the corresponding number of this factor into our function. And if it equals 0, then it's a factor. If it's not, then it's not a factor. Okay, so let's do this. So the corresponding number for 2x plus 1 is negative 1/2. Negative 1 over 2. So let's try subbing in negative 1 over 2 to our function. Over 2, 3, minus 9, negative 1 over 2, 2 minus negative 1 over 2, plus 3. Okay, this equals to, so that one is Okay, so in this case, we do actually get 0. Alright, so this means, since negative 1 over 2, we subbed in, we got 0. That means that 2x plus 1 is going to be a factor. So, yes. Alright, so for b, we just do the same thing. There should be an equal sign between here. So our function is 2x3 minus, oh wait, okay, let's just substitute it in. Okay. So if we want to see if 2x plus 1 is a factor of our polynomial here, then we just have to substitute this guy, or a corresponding number, into our function. If it gets us 0 like last time, then yes, 2x plus 1 is going to be a factor. Okay, so let's do that. Equals 2, 2, 1 over 2. Minus 6. Okay, so let's just see what it comes out to. Alright, so we didn't actually get 0 this time, we got negative 8. That means that 2x plus 1 is not a factor of our function, and the remainder of this is going to be negative 8, because the remainder theorem also says if we sub in this number, b over a, it will actually give us the remainder when we divide these two together, 2x plus 1, with our polynomial here. So yeah, since we plugged in negative 1 over 2 into our function, this guy is going to be our remainder if we did divide these two polynomials with each other. So there we have it. That's number 1. Alright, we have another example here. When x cubed minus 2x squared minus kx plus 6 is divided by x minus 5, the remainder is 11. So our job is to find the value of k in our polynomial. So we're actually given that when we divide these two guys together, so I'm going to do this in green. When we divide these ones together, we actually find our remainder is 11. So that's what we're given. So you're wondering how can we use this information to get an idea how to solve for k, this guy over here. So we can use our remainder theorem. Our remainder theorem tells us that if we substitute a number in here, it will give us a remainder when we divide these guys together. Meaning, since if we divide this with this, the remainder is 11, that means that if we substitute the corresponding number of our factor here, which is 5, if we substitute that within our function, it should give us the remainder. And since we know that is 11, that means that we know that f at 5 equals to 11. This comes from our remainder theorem. And it makes sense, right? So 5 is a corresponding number to this. And since we're given that when we divide this polynomial with this gets us 11, that means if we substitute 5, the corresponding number to x minus 5, into our function, we should get 11 as our remainder. Okay, so you might be wondering how this thing is going to help us solve what k is. So, in this case, we're substituting 5 into our function. And then if you can kind of foresee what's coming up next, all our x's are going to become 5s. And the only variable left is going to be k. So in that case, we can actually solve for k and determine what the k value is using an algebra. So let's do that. Let's do the motion. So we substitute 5 in. We have 5 cubed minus 2, 5 squared minus k times 5 plus 6 equals to 11. Okay, so then we can just simplify all this stuff. 50, 5k plus 6 equals 11. Alright, so if you notice, we have an equation here with a bunch of numbers and one variable k. So if we collect all our like terms, and we solve this just like how we usually do, then we can determine what k is. Okay, so we have here 75, negative 5k, okay. Equals 70, then k equals 2. To 14. Sweet, there we go. K equals to 14. And we're done. So I guess in overview, because we know we divide these guys together, it gets us 11. Then from remainder theorem, we know that if we substitute 5 into our function here, it will give us the remainder, which should be 11, based upon what we were given in the question. And we use this to our advantage, meaning since we know f of 5 equals 11, that means if we substitute 5 into our polynomial here, it should get us 11. And then we found k by solving the equation that was created, that we magically created. Okay, that's it. So let's do some more examples. This is number 3. The polynomial mx cubed plus 12x squared minus x plus 2 has a remainder of 14 when divided by x minus 1. And has a remainder of 68 when divided by x minus 2. What are the values of m and n? So this looks very similar to the question we had before, where in our polynomial we had something we didn't know. Last example was k, and what we did was we used remainder theorem to figure out that we can create an equation with k and then solve for it. So this is a little bit similar, even though we have two pieces of information that we need to find, m and n. Okay, so you might be wondering what we can do here, but we'll just start off with what we know based upon remainder theorem and factor theorem. Okay, so the first thing we know is that when we divide by x minus 1, you'll get a remainder of 14. So if you divide this by x minus 1, we'll get 14. So based upon that, we can use remainder theorem, and we can deduce that f at 1 would equal to 14, because, yeah, the number corresponding to our factor x minus 1 is 1. So we know if we plug in 1 into our function with remainder theorem, we will get 4t based upon remainder theorem. So we know this. F at equals to 14. So it's not very clear how this would help us, but let's just roll along with what we found out here. So if we have f at 1, that means that we plug in 1 into our equation over here at the very top. So let's do that and see what happens. Okay. So m1 plus 12 is 1 minus n. Okay, so we know this thing can equal 14. So that means we have n plus 12 minus n plus 2 equals to 14. And let's just keep going. Now, don't know where this is headed, but we can at least simplify everything first. So we have n plus n equals, oh, nice, 0. Okay, so we have this thing. M minus n equals to 0. So what does this mean? So here we have, an equation with two variables and two unknowns. We didn't really get any closer to figuring out what m and n are, but this should raise an alarm in your brain. Meaning, we have an equation with two unknowns. That means that if we have another equation with also m and n in it, then we can use system of equations or substitution to figure out what m and n are. And to get our second equation, notice how we got this equation by using this fact at the very beginning. We use the fact that when we divide x minus 1, we get a remainder of 14. And then using that information with the remainder theorem, we were able to say that f at 1 equals to 14. And then we were able to get our equation here by doing some algebra. So if we do something similar, then we can get a second equation with also m and n, and then use systems of equations to solve for those two variables. And the big question is, where are we going to get it? Well, we still have more information to work with. We also know that it has a remainder of 68 when we divide by x minus 2. This means we can use the exact same logic as we did before with this guy. Since the corresponding number for x minus 2 is 2, that means from our remainder theorem, if we substitute 2 into a function, then it should give us a remainder when we divide those two guys together. In this case, it will be 68. Therefore, we know that f at 2 equals to 68. Then we'll do the same thing. So m at 2 cubed plus 12 minus n2 plus 2 equals to 68. Awesome. I'm going to erase this thing over here. Okay, so we have 8m plus 48 minus 2n plus 2 68. 8m minus 2n. That's just some algebra we got to do. Collect our terms. 18. Fantastic. Sweet. So, go over here, our result. We have two equations, two unknowns. So we can use substitution. We can take one equation, solve for m or n, and then substitute that into our second equation to find m and n. This is just the process of systems of equations. So, yeah, we're going to do that up over here. So we're going to erase this work over here. Actually, no, you don't have to do that. Okay, let's just work down here. So we have m minus n equals 0. Okay, so the process for this, you just have to choose one of the equations, isolate it. In this case, it's very easy to isolate for this guy, because that means m equals to n. Then we substitute that into our other equation. So you have 8m oh, I'm going to replace it with n, right. Change this. So since we know m equals to n, we can replace all our m's in our second equation with n's. So it becomes 8n minus 2n equals to 18. We have 6n equals 18. N equals to 3. Which also means m equals to 3. If we substitute that into our second equation. And there we have it. We are done. So just to reiterate how we kind of went about this, in the beginning, we still use the same concept as before for remainder theorem. Nothing really changed. So we know that if we divide x minus 1 with x minus 1 into our polynomial, it'll get us 14, which means from remainder theorem, if we sub in 1, our corresponding factor, then we will get 14, because of what remainder theorem says. So we knew f at 1 equals to 14. And then we substituted 1 into our polynomial here. And at the end, we achieve this equation over here. Oh, I forgot the 0. We achieve this equation over here, n minus n equals 0. So even though we weren't able to get the values of m and n, we know that if we had a second equation similar to this for m and n, we can use substitution to solve for both of them. And that's what we did over here. We were also given the fact that if we divide this polynomial by x minus 2, we'll get 68. So we kind of did the same thing. From remainder theorem, we know that if we substitute 2 into our function, then we should get 68, which is our remainder. And with the same process, we achieve this equation. Then down here, we have m minus n equals 0, 8m minus 2n equals 18. We're able to do systems of equations to solve for both m and n. And this is just the entire process of doing so. And there we go. That's example number 3. All right, so example number 4. When 3x squared plus 10x minus 3 is divided by x plus k, the remainder is 5. Ooh, let me fix this up. Okay. Determine the value or values of k. All right, so this kind of looks similar, and I guess. So we don't know what k is. That's our job, to determine the value of k. But instead of it being in our polynomial, it is in our factor that we're dividing with our polynomial. So how can we go about this? Big question. So we can actually use this, or you can actually use remainder theorem in the exact same way as before. So we know that if we divide this by x plus k, we get 5, which means if we substitute the corresponding number for a factor into a function, it should equal to 5. The big question is, what's the corresponding number to x plus k? Well, if we kind of do some trial and error, let's pretend k is numbers like 1 and 2 and 3. So if k was 1, so let's pretend k is 1, then the corresponding number to our factor x plus 1 would be negative 1. So and then if we change it to 2, it'll be negative 2. If we change it to if we change k to be, I don't know, let's say 8, the corresponding number would be positive 8, so on and so forth. So you can kind of see a pattern here between our number k that we kind of replaced to what the corresponding number is going to be. It's just going to be the negative version. So if we have x plus k, that means the corresponding number to this factor would just be whatever k is, but the opposite sign. So in this case, negative k. So negative k is going to be our corresponding number, whatever k is going to be. So how is this going to help us? Well, we know that if we substitute a corresponding number to our factor into our function, we will get the remainder. So that means that if we substitute in this number, negative k, into our function, that means that it should equal 5, whatever k is going to be. So we're going to write that out actually. So that means that f at negative k, whatever k is, should equal to 5. So let's continue on with this. It's not exactly clear where this is headed, but we know that if we substitute negative k into our function, 3x squared plus 10x minus 3, we should get 5. So let's just keep going with that. So we have negative k squared plus 10 negative k minus 3 equals to 5. So we have 3k squared minus 10k minus 3 equals to 5. Alright, so we're going to pause here. So when you're doing these questions, it's also nice to know that, like, if you're trying something out and you're working with something, it's always nice to just step back for a while and kind of see what we have. And then stepping back and seeing what you have can help you determine what the next step is going to be. So in this case, if we take a break here and we take a look at what we have, if you notice, we have 3k squared minus 10k minus 3 equals to 5. So this looks like a quadratic equation with k's because we have a k squared term over here, and then the rest of our terms here are less than degree 1. Less than degree 2. So we have minus 10k minus 3 equals 5. So this is a very good indication that we do have a quadratic equation, and to solve for the value of k, we just have to treat this like a quadratic and solve it like how we usually solve quadratics. And how we do that is we need 0 on one side and everything else on the other side. So let's do that. Okay. Awesome. So we have this. Great. 3k squared minus 10k minus 8 equals to 0. So we can either put this into our quadratic formula to get k, or we can factor it using whatever quadratic method that you choose. I'm just going to do this in my head. All right. So what factors work here? 4. I'm thinking. Okay, we need 3k here. We need k here. So, negative 4 and positive 2. There we go. That means that k is going to be either 4 or, negative 2 over 3. There we go. We did it. Alright, so just to reiterate how we kind of solve this problem. So our job was to find out what k is. And k is the value in our factor here. And even though k is in a different spot, we can still use remainder theorem, meaning we know that if we substitute the corresponding number for x plus k into a function, we should get 5. This means that f at negative k, since negative k is the corresponding number to this guy, if we substitute negative k into a function, we should get 5. And then we kind of went about this like before. Nothing really changed in our process. It's just now we're substituting in negative k in here. And you kind of simplify things. And then we noticed that once we got to this step, we have a quadratic equation over here. So in order to solve for our k value, we just have to solve this like a quadratic equation. And yep, 0 on one side, everything else on the other side to get a quadratic. We factored it over here, and then we got our values of k. So yep, we use the remainder theorem in the same way, but the way we solved it is a little bit different, but the concept is still the same, especially this step right here. Okay, awesome. That's number 4. All right, here's our last example. So number 5, for what value of b will the polynomial negative 2x cubed plus bx squared minus 5x plus 2 have the same remainder when divided by x minus 2 and x plus 1? Okay, so we can do this. Our job is to find the value of b. And b is some unknown in our polynomial here. So we're not really given what the remainder is, but we know that if we divide our function with x minus 2, then the remainder is going to be the same as if we divide our polynomial with x plus 1. So how will that help us? How can we use remainder theorem to do this? So let's just figure out the corresponding numbers to our factors here. That's a good place to start. So we know this guy is going to be 2. This guy is going to be negative 1. Alright. So even though we're not given what the remainder is, we know that the remainders are going to be the same between these two. So that means that in our remainder theorem, because we get the same remainder, if we compare f at 2 with f at negative 1, they should be the same, right? we know that these two things will be equal to each other because we know that f at 2 gives us the remainder when we divide f of x with x minus 2. We also know that this gives us a remainder when we divide f of x with x plus 1. And since these guys have the same remainder, that means that these two values, since they both give us the remainder, would be the same. So that f at 2 equals to f at negative 1. So yeah, let's proceed. Let's just substitute 2 into a function, and we'll get some nice equation over here. So we have 2 at 3 plus b, 2 squared, minus 5 at 2 plus 2 equals to the same thing, but we're subbing a negative 1 instead. Alright, good stuff. So let's simplify things. This gives us negative 16 plus 4b plus, oh wait, not plus, minus 10 plus 2 equals 2 plus b plus 5 plus 2. Okay, so if you look at what we have, if we step back, we have a bunch of numbers. We also have b as a variable. So this is just like a normal linear equation where we just need to put all the variables on one side, all numbers to the other side, and we can solve for b. Okay, let's do it. So we have on this side 4b. Negative 16 minus 10 is negative 26. Plus 2 is minus 24. Equals to b plus 9. Alright, so 4b minus b equals to 9 plus 24 equals to 36. b equals to 12. Awesome! And there we have it. There's our final answer. So just to reiterate what we did here, since we know that if we divide this guy with x minus 2, the remainder is the same as if you divided function with x plus 1. That means that f at 2, which gives us a remainder of f of x divided by x minus 2, should be the same value as f at negative 1, since this also gives us the remainder if we divide these guys together. So that means we knew that these two values would be the same. And then after this, we just substituted 2 into our polynomial to get like a nice long equation over here. And then we simplify things. We can solve this by moving all the b's to one side and all the numbers to the other side, which is what we did here after we simplify some of these numbers. And there we go. We found the value of b. That's all there is to it.